a homogeneous equation is essentially a separable equation in disguise, because any homogeneous equation can be turned into a separable equation. If we have the first order differential equation, m of xy dx plus n of xy dy is equal to 0, that's homogeneous if both m and n are of the same degree, such that you have the following situation. So for m, we have m of t times x, comma, t times y. That is, we substitute tx, so to speak, for the x, and the ty, so to speak, for the y, and then we end up in a situation where we can factor out the t to some n power, and that's multiplied by our original function, namely m of xy. And likewise, for n of tx, comma, ty, we're able to factor out the t to n power, and that's multiplied by our original function, n of xy. So here we have degree n. If you have a situation like this, you can substitute. You can substitute y is equal to ux, where the derivative by the product rule is dy is equal to u dx plus x du, and that's just the product rule. So you can turn any homogeneous equation into a separable equation. And we can prove that the following way. And in the next video, I'll do a concrete example running through the proof, but with a particular example, whereas this is very general, so there's a lot of variables, and that's sometimes confusing to look at. But in any case, we can prove this. So proof by hypothesis, both m of xy and n of xy are homogeneous of degree n. We can rewrite our general homogeneous equation as a separable equation with u is equal to what? Y over x. So we're going to do a substitution. So by using the general form of the homogeneous equation and showing that by a certain substitution we can then get something that's separable, then we have proved that all homogeneous equations are separable. So the first thing to note here is that for m of xy, we're going to say this is equivalent to x to the n power times g sub 1 of u, because we're saying that u is equal to y over x. The key here ultimately is that we're able to factor out x to the n power, and this ultimately allows us to separate our variables. Otherwise we couldn't do it with a homogeneous equation. Okay. And n of xy is going to be equivalent to x to the n power times g sub 2 of u. And again, we're able to factor out x to the n power. It could also be y to the n power. Okay, same kind of idea. And then we can rewrite our general expression for our homogeneous equation as x to the n power times g sub 1 of u dx plus x to the n power times g sub 2 of u. We can't use dy here. Instead we'll use u dx plus x du equals 0. First thing to notice, again, is that x to the n power. If we divide everything by that, it goes away. Okay, we simplify our equation. So we get g sub 1 of u dx plus g sub 2 of u dx plus x du. is equal to 0. And then I think the good idea would be to expand this out, this expression. So we have g sub 1 of u dx plus u times g sub 2 of u dx plus x times g sub 2 of u du is equal to 0. Here's a dx expression, here's a dx expression. So we could group those together to get g sub 1 of u plus u times g sub 2 of u dx plus x times g sub 2 of u du is equal to 0. And if you look closely, this is definitely separable. We'll divide everything by g sub 1 of u plus u times g sub 2 of u and then we'll divide everything by x. And then we get dx over x is equal to, let's see, g sub 2 of u over g sub 1 of u plus u times g sub 2 of u du. And I'm sorry, just by habit, I haven't moved anything to another side of the equation. So this is plus equals 0. And then I could move something, so I'll just say g sub 2 of u over g sub 1 of u plus u times g sub 2 of u du is equal to minus dx over x, and then we could integrate. So here is our separated equation. And this is a very generalized form, so we have proved that every homogeneous equation ultimately is separable. In the next video, I'll do a concrete example, but at the same time, I'm going to go through this proof, so this will give this proof a lot more life, I think. And then it will make sense why this substitution works.